So we spent a whole heap of time recapping algebra, and now we've talked a little bit about numbers, their building blocks, the prime numbers, fractions, and so on. So basically what we've talked about so far, if you like, can be thought of as the alphabet of mathematics. Relations and functions then are maybe like the words, how we put the alphabet together and use it and come up with mathematical sentences and theorems and formulae and what have you. So let's define it. A relation, very simple definition. If you imagine a set of ordered pairs, you've got two values and they are simply related in some way. If I look over here to the left here, I've got some graphs on the wall. They're all relations. We know that because of the equation. There exists a relationship between the y value and the x value. You've got y equals x squared, y equals 1 on x, and so on. So they are all relations. So a circle, x squared plus y squared is 25. Now, a function, which we're a little bit more interested in, is a specific type of relation. And it has to be such that for any x value, there's a maximum. There can only be a maximum of one possibility for the y value. Okay? Now, the hyperbola is okay. You might be looking at x equals 0 and go, oh, hang on, there's no y value. That's all right. You just can't have more than one y value. And that's what we would call a function. So y equals x squared, the parabola, is a function. It doesn't matter which x value you pick, you're only going to get one y value. Simple way visually to test to see if something is a function or not is what we call the straight line or the vertical line test. Imagine grabbing your ruler and just sliding it vertically along the picture. So long as that ruler only hits the graph once, it's okay. As soon as it hits the graph twice, no good. It's not a function. So that's a visual way of testing. So again, let's use the hyperbola. Y equals 1 on x. We can slide it along. It does not matter where I draw the vertical line in. It will only hit it once, if at all. So y equals 1 on x is a function. What about, here we go, sideways parabola, x equals y squared. If you start at the left, everything's okay because it's not hitting any at all. You get to the y-axis, it's still okay because it's only hitting one value, but as soon as you get into those positives, no good. Hits it twice. So that one would be a relation, not a function. And you usually find relations we can break up into two functions that make the relation. And in this case, the top half would be y equals the positive square root of x, and the bottom half would be y equals the negative square root of x. So they're the two functions that make up that relation. Right, so domain and range, a couple of important concepts. Domain, if you like, if you've got your function, is the input. These are all the values you put into the function. So every possible value of x that you could substitute in and get an answer. It's usually easier, when you're trying to find a domain, it's usually easier to look for values that x cannot be rather than it can be. Because you can then look for specific things. Now, if you've got a picture, domain and range is dead easy because you can just look at the picture. So again, there's our sideways parabola. Well, it's a relation, but we can still talk about domain and range. And we're looking for values of x that will give us y values. And so we can clearly see from that picture the domain is x is greater than or equal to 0. We can't substitute in a negative number for x and get an answer. Sometimes we have these split functions, step functions that we have where there's gaps in it. So the domain for this one would be x is less than or equal to 0, because the dot's coloured in there, and x is greater than 2. So they're the ones that are giving us y values. So what to look out for if you don't know what the picture is? Okay, think about fractions. If there happens to be a fraction in it, key thing about a fraction, we know the bottom of the fraction cannot equal 0. So that will cause problems when we're substituting numbers in. So if it was y equals 1 on x and for some insane reason we don't remember what it looks like, oh geez, y equals 1 on x. So you look at the bottom of the fraction and we go, well hang on, bottom of the fraction can't equal 0, so I know x can't equal 0. Everything else is okay. Now when you write a domain, Remember, it's the values that are in the domain. So I would write it something like this. I'd say, well, my domain then is all real x, every single possible value except the value x equals 0. I can't have the value x equals 0. So domain, it's an inclusion. So what's included? Now, there are different ways of writing this, and I guess it all comes down to grammar. Because I could put all real x except x cannot equal 0. So do I put equals to or not equals to? And again, it just comes down to the grammar. Because if you think about it, I'm saying, hey, all real x except x equals 0. Can't have that one. Or I might be saying, all real x, except x can't equal 0. It's really pedantic, and it doesn't really matter, I suppose, as long as you're making it clear the value that it cannot be. So how you write that one is up to you. The thing you definitely don't do for domain is write x cannot equal 0. Because all you're telling me there is I would say, oh, okay, it can't equal 0, but what can it equal? You're not telling me what it can equal. And the other word that's important there is real, because we're dealing with real numbers. Now, okay, at this stage the only numbers we know are real numbers, but there are other types of numbers as well. So we specify it's all real x. Let's have a look at this one. So again, we see the fraction. What's causing me the problem? Well, the bottom of the fraction can't equal 0, so I know x in this case can't equal plus or minus 1, so I have all real x except x equals plus or minus 1. What happens if I have two fractions? Well, it doesn't matter. Got to look at both fractions because I can't have 0 in either of the fractions. So x minus 1 can't equal 0. 1 would cause me a problem. And 7 minus x is going to cause me a problem as well. So x can't equal 7. So I've got two values there. So all real x except x equals 1 and x equals 7. Okay, the other thing to watch out for, square root signs. Well, I suppose it doesn't have to be square root. Any even root. Now, odd roots are fine. You can find the odd roots of negative numbers. You can find the cube root of negative 3, or well, you can't find it exactly, but you can find the cube root of negatives. But positive roots, you can't. Now, we're pretty much only going to see square roots, but you can't find the square root of a negative number. So y equals the square root of 4 minus x squared. So you might not recognise it straight away. Fingers crossed, hopefully we do. What am I looking at there? Semicircle, yeah. So it's actually the top half of a semicircle. But okay, we don't recognise it. So we'd say to ourselves, well, look, I've got this square root sign. I know 4 minus x squared has to be greater than or equal to 0. So that means x squared is less than or equal to 4, so x must travel in between minus 2 and 2. Now in this case, it's automatically given me an inclusive domain. X is in between minus 2 and 2. If I have two square roots, again, I'd have to deal with both. So I know x has to be greater than or equal to negative 3. I also know it has to be less than or equal to 5. Now, is this an or an and situation? And. Both must be true. So if both must be true, then my domain would be x is in between minus 3 and 5. They're the only numbers that will work for this one. Oh, combination of the two. I've got a fraction, but I've got a root sign as well. So normally I'd say, well, the bottom of the fraction can't equal 0. But not only that, now I know what's under the third sign has to be greater than or equal to 0. So I can sort of combine that into one thing and just say, well, instead of saying greater than or equal to 0, can't be equal to 0. So it's x plus 2 is greater than 0. And we get x is greater than negative 2. So they're the sorts of things to look out for. Now, range. Range then is the output. Okay. So once you've used all the domain, once you've substituted in every possible value, what answers did you get? What were the y values? Okay. So it's the output. So let's have a look again visually. Brilliant. We can just look at it and we can see that actually every y value is possible on that one. There are no gaps vertically at all. So all real y. The step graph there, we'd have y is less than or equal to 1 and y is greater than 3. But again, what happens if we don't recognise it? haven't got the picture. So I suppose when we're talking about range, things to look for are things that are obviously going to cause a maximum or a minimum. It'll stop the curve going up or going down. So things like even powers, absolute values, they're going to stop things being negative. So we know they're always going to be greater than or equal to 0. So parabola, for some reason we don't know what it looks like. Y equals x squared. But hang on. I know x squared always has to be greater than or equal to 0, so therefore I'm only going to get answers that are greater than or equal to 0, so that's got to be my range. Y is greater than or equal to 0. So logically then x squared plus 3, well in this case it's got to be greater than or equal to 0 plus 3, because the x squared is going to be greater than or equal to 0, and I'm always adding 3 to it, so we get y is greater than or equal to 3. Of course that's our parabola that's been shifted up 3 units. So again, if you know the picture, much easier. 5, but we're subtracting the x squared. So we're subtracting something. So negative x squared now actually is always less than or equal to 0. So y will always be less than or equal to 5 minus 0. So this curve will always be less than or equal to 5. Absolute value of x plus 2, well, again, can't be negative, so that one's going to be y is greater than or equal to 0. If I had, well, again, if I shifted it down 5, well now I know the range will be always greater than or equal to negative 5. So range is, I suppose, a little bit trickier. What some people do, because domain is usually easier to find than range. So what some people do is swap the x and the y value. Okay? So let's say y equals x squared, and make it x equals y squared. And then instead of finding the range, find the domain of the new one. You see? So it's playing with inverse functions basically, which we'll talk about inverses later. But that's what some people do when they're a little bit unsure. They'll swap the x and the y around, and instead of trying to find the range, they'll go and try and find the domain of that new function, which will be the range of the original function. What happens if there's restrictions on the domain? Okay. This is like one of those, and you've probably heard the expression before, don't know where it originally came from, but a rule of thumb. What I usually do, because it's amazing how often these things are symmetric. And so, if you've got a restricted domain, I always look at the endpoints and the middle and see what sort of y values are being given to me. So there's our semicircle, but we don't know it's a semicircle. So minus 2 to 2, it's restricted between. So I'll have a look at positive 2. That gives me a value of 0. Did I worry about negative 2? Because when it's squared, it's going to give me the same answer of 0. Look at the middle, 0. It gives me an answer of 2. So it's pretty fair bet that that range is going to give me values between 0 and 2. Fractions, how's that going to affect range? You cannot divide a constant by 0. Right? We know that. So if you have a constant on the top of the fraction, the answer can never be 0. Because you can't go y divided by something is 0 either. So as soon as you see a fraction on the top, constant on the top of the fraction, that fraction you know cannot equal 0. So back to our hyperbola, values of y, I know, well hang on, I'm never going to get an answer of 0. I can't go y divided by something and get an answer of 0. Can't happen. So y can't equal 0, so all real y except y equals 0. 5 plus 1 on x then, I'd look at that and say, well I know the fraction can't equal 0. So I'll never get 5 plus 0. So all real y except y equals 5. Ooh, not immediately obvious. There's not a constant on the top of the fraction here, but I could rewrite that. X plus 7 on x plus 4, I could rewrite as 1 plus 3 on x plus 4. Now I've got a fraction with a constant on the top. I know that fraction can't equal 0. So therefore, Oh, just doing the division to the side. If you weren't immediately sure how I got 1 plus 3, I'm going, x plus 7 divided by x plus 4. X goes into x once. Do our subtraction. You remember polynomial division? There we go. Remainder of 3, hence I could write it as 1 plus 3 on x plus 4. Mind you, hopefully those quick ones you just do without division, but it's always there if you need to. So y can't equal 1 plus 0, or real y, except y is equal to 1. A bit about function notation. Instead of writing y equals, sometimes we just say the function equals, because the y value is the function, if you like. So y is, and we often write function x, and I guess that's why f's there, f standing for function. It doesn't have to be f, it could be any letter you like. So if we get something like function 5, it's simply saying substitute in 5 for x and you get 79. Of course, you don't have to substitute in a number. I could say, what's function a? Wherever I see an x, I replace it with an a, so it's 3a squared plus 4. In fact, you could see something like this, which we will see a lot of later in a particular topic. We could get function x plus h minus function x. So, all right, everywhere I see an x, I replace with an x plus h minus the actual function itself, expanding it out, grouping like terms, and there we go. 6xh plus 3h squared. Alright, so today we shall look at 2f. In fact, I'm feeling so generous that you can have till Monday